This is the fifth lecture of the Power Engineering module EE114, and this is based on transformers. Let's begin. So we'll first talk about an ideal transformer. Ideal means that technically it doesn't exist in real life, and you can imagine that it would be very simple to handle, and it will form the basis for a real transformer. So basically, an ideal transformer is just is simply a magnetic circuit, and it has two coils. That's it. Now, here are some assumptions that we take while we are talking about ideal transformer. The assumptions are that it has infinite permeability. The core has infinite permeability. There are zero hysteresis losses. There are zero eddy losses. And all the flux is confined to the core, and all of it links both the coils. So what does that mean? There is no air leaking. There is no flux leaking out into the air, and all the flux that passes through one coil also passes through the other coil. So this is what the magnetic circuit would then look like. Right? All the flux is linking both of them. Now observe that this is N1 times d phi by dt, the voltage across the primary, and as you can see, I have shadily taken care of the minus sign. Now that minus sign is not disappeared, what we are actually doing is we are taking care of the minus sign later. We will just decide the polarity such that there is no minus sign. We will reverse the polarity. This is something common in electrical engineering. If you see a minus, instead of taking care of it, what you do is you will decide the polarity later. Similarly, eating the minus, V2 is N2 d phi by dt. D phi by dt is same because phi is same, and hence V1 by N1 is V2 by N2. Right, so this is the stepping up or stepping down of the voltage. What ratio does it happen in? Well, V1 by V2 is N1 by N2. And since this is true at any point of time, if you put in a sinusoid, that would also work. And hence, technically, in phasor form, this works. So you just put tildes over here, and that's it. Now we talk about the infinite permeability thing because that hadn't come into picture yet. See, if there was infinite permeability, that's like saying I have a wire and I have two batteries, right? There is one battery, there is another battery. And I am saying that obviously there cannot be any net voltage drop across the wires itself. Hence the battery voltages must be same. Now obviously these are not batteries, they have currents, and hence the currents can adjust themselves such that N1 I1 is N2 I2. This is the net MMF drop across the magnetic circuit, which has to be 0. So I1 by I2 is N2 by N1. And a very nice thing that is now happening is that V1 I1 over V2 I2 is N1 and over N2 into N2 over N1, which is 1, which means that the power that is being pumped in is the same as the power that is being pumped out. Now this means that the power remains same in both sides. And hence phasor power also remains same because it is derived from the time domain power. And this should be the case because that's what we said. There are no hysteresis losses, there are no eddy losses, there are no losses. So since there are no losses, the power is same. Now there is an important concept of referring quantities that we will talk about. So it is helpful to think that somehow we could pick up a component from one side and then put it on the other side, and there would be some scaling or there would be something that we can do such that the circuit would remain same. The currents and the voltages would remain same. If there was some transformation we could do such that we could transfer appliances from one side of the transformer to the other. So this is called referring of one thing from one side of the transformer to the other. What is the thing? It could be an impedance, it could be a resistance, it could be current, it could be voltage, it could be a source, it could be anything. Each quantity has a different ratio, and that depends on the turns ratio. So the turns ratio is that ratio called N1 over N2. Now we know that V1 over V2 is N1 over N2. Hence, voltage gets scaled N1 over N2 times when you go from the secondary to the primary. Hence, voltage sources, when you refer them, have this turns ratio simply. The current source has N2 over N1. So it's the opposite. Now V over I is N1 square over N2 square. So this is the ratio by which the impedance gets scaled. And note that once again power is remaining same. So you don't need to refer power, power will remain same. And this N1 over N2 quantity is called A. So voltage has referring ratio A, current has 1 over A, impedance has A square. Now we start throwing in the non-idealities. So the first non-ideality we deal with. Not all flux links both coils, which means that the permeability is not infinite, there is some leakage. But now comes an important part. This escaped or this leaking flux returns through air, right? Because it can't reverse the direction midway inside the magnetic material and then return through the magnetic material. If it wants to return without going through the magnetic material, it has to go through air. And we know that air has no hysteresis in it. We know that air has no eddy current loss in it. And we know that air has constant permeability. So this is excellent because that leak flux is now simply acting like an inductor, right? So it is depicted as a self-inductance in series. Now we know that the inductance has value n square over reluctance. What is this reluctance? This is the reluctance of the path in air that this escaped flux is following. Obviously, you can't actually trace that path because it is in air, but you can find a self-inductance. We will see how it is done using something called a test. We will see how you conduct tests on a transformer. Now, while we are on the topic of putting things in series with the transformer, we know that the winding of the transformer, the copper winding, it's not exactly saint-like. It also has a resistance. So you put that in series as well. Now the magnetization current, this is the second non-ideality. There is a magnetization current because until now we had been talking there is no MMF drop across the magnetic circuit. But this is a real circuit now. It does have a MMF drop. Since it has a MMF drop, that means that there is some current that is going into setting up that magnetization. There is some power going into it. There is some hysteresis happening. There is some eddy loss happening. And we saw that this part can be modeled as an inductor and resistor in parallel. So now here comes the important point. We know that if we pass the magnetization current through a branch which has an inductor and a resistor in parallel, we know that we have modeled it correctly. But we don't know the magnetization current's value because there is one current going over here, there is some current going over there. But generalized machine theory proves that the magnetization current has this value over the primary side. If we shift this to the secondary side, it will become N1 over N2 I1 minus I2, and you can see that this is then symmetric, right? So that's why magnetization current at the side of the winding you're talking about is this. So this is actually a generalized machine theory result. So final equivalent circuit, what we do is we place this magnetization branch then as a diverter before the rest of the current goes into an ideal transformer. So what we have done is we took the real transformer and first of all we snapped out the self-inductances, we snapped out the resistances. Now we are left with a transformer that does not have any leakage but it still needs magnetization. To account for the magnetization, I took the difference between the current and the referred current from the secondary side, because this is the referred current from the secondary side, this is the current from the primary side. The ideal transformer would obviously give this referred current of the secondary side, so the difference would flow into the magnetization branch, and so that difference has simply flow through here. Now this is the most important diagram in transformers. This is the equivalent circuit. So let me explain what I was talking about, the referred currents, right? I have some current I1, and since this is an ideal transformer, the current through this is I2 getting referred, that is shown by this symbol at the top, I2 prime. Now I2 prime is N2 over N1 I2, and the difference between these two currents is what is flowing through here. So if in this branch I have I1 minus N2 over N1 I2, I could simply put the magnetization branch here and be done with it. This is actually a very nice coincidence that we are getting. It might have not been there, it is not so obvious. The fact that we are able to do this is actually great. This is actually helping us a lot that this is happening. Now we come to some standard results about transformer. By result I mean it is some standard rating of a transformer. The first is called the regulation. So what is voltage regulation? You want the voltage to remain fairly constant as the load changes, right? So the transformer should be able to do that. So voltage regulation is the change in the voltage across the terminals of the secondary when you go from full load to no load, keeping V1 constant. Now this is some term That confuses a lot of people. What is full load? What is no load? Remember that load means that there is some load that is coming onto your circuit. The circuit now has to provide power. So simply speaking, load means the power that is going in output. That's it. So full load is the maximum power that the transformer could possibly throw in its output, and no load means that it is open circuited, so there is no load. Now this is the formula for the regulation of voltage, and if someone asks you to find the regulation of this transformer circuit, all you have to do is first put no load, right? So that would be V20, the terminal voltage across the secondary when there is no load. Then put full load and then divide by this full load again. This is the formula for regulation. Most transformers have a regulation in the range 1.5 to 3%. That's it. Now this is usually shown as a percentage. You multiply this by 100, right? Now comes efficiency. It is the ratio of the power that is supplied to the secondary or to the load and the power supplied to the primary. So the typical formula for efficiency is 1 minus losses over input. Now how to find the transformer components that will be utilized in these formulas, that self-inductance of the primary winding, the resistance of the primary winding, and the equivalent inductance of that magnetization branch. We should be able to actually numerically calculate it by passing some nice current and voltage. That is called a test. So there are two tests. The first test is called an open circuit test. This is usually done from the low voltage side. What is the low voltage side? It is the side of the transformer with the lower number of turns. So it is at the lower voltage. You supply the rated voltage at the lower voltage side and you open circuit the higher voltage side. There is no nothing there. Now you measure the current that you're supplying from the low voltage side and the power that the low voltage side is now drawing. Observe that usually in such circuits, usually in the circuits for the tests, we make one or the other assumption. So while in the open circuit test, we see that the magnetization branch actually has a large impedance. So what we do is we ignore the impedance of the primary or the low voltage side. All we do is take the impedance of the magnetization branch and that's it. So you are given the voltage, you are given the current, and you are given the power. That allows you to completely determine the impedance of this magnetizing branch. The second test is the short circuit test. In this, it is done from the HV side and you supply rated current and you short circuit the lower voltage side. So you apply the rated current from the HV side, you are short circuiting the lower voltage side, and now you are measuring the voltage across the HV side and the power across the HV side. Here, since the magnetization branch has a very high impedance and and there is a parallel path available through the low voltage side, which is very small actually compared to the magnetization branch. It has a very small impedance. So here we ignore the magnetization branch and we say that the impedance of the primary or secondary are all that are coming into picture. Now, technically, this is the most that you can get out of these two tests, but then there is an assumption that says that you take the impedance of the primary and the referred impedance of the secondary as equal, right? So you take Z1 and A square Z2 because we are referring it. You take Z1 and A square Z2 as equal, and then you can find out all the things. So now I will try to explain once again because you didn't have the picture yet. So when you do the open circuit test, what happens is you are doing it from the low voltage side and this all is not there. This is open circuited until this part, and from here onwards is the circuit, right? And this magnetization branch, yeah. So this is not there and this is much less compared to this. So you say that almost all of the impedance is measured by this because a very small thing in series doesn't matter, right? Now in a short circuit test, what you're doing is the load is short circuited. That's it. So what happens is you say that there is a very small impedance here, a very high impedance here, and then again a small impedance here. So these two are in parallel, right? So since there is an ideal transformer here, you first refer it to here, you get A square Z2, and then you say that A square Z2 is very much smaller than this magnetization branch, so all current flows through that. So now we have got Z1 plus Z2, Z1 plus A square Z2. You set them both equal to each other and you have got all the components. Now comes a rather neglected part of a transformer, that's the inrush current. So what is an inrush current? Say when you start a transformer, the EMF and flux both rise from zero, right? But the EMF was the derivative of the flux. So when you are applying some EMF, the flux is like the integral of EMF, tries to go up. But observe that flux should technically be 90 degrees out of phase, right? So it should actually be the most negative extremum at the starting, but it is actually at zero. So instead of going at the top value, it crosses that, and like a typical sinusoid that is starting from zero, actually, it goes up and it crosses, it becomes double its usual value. So it becomes a bit like the graph of sine square t, if you have seen it. So now the flux doubles, right? Instead of normal flux, there is double the flux, there is double the B. But if you double B, you know, you need much more H to double B now, because the material is actually getting saturated. The material is not built to handle double the B. It is simply made to handle some 1 Tesla, 1.5 Tesla. It is not meant to handle 3 Tesla. If you start flowing 3 Tesla, you are going to need about 20 to 30 times H. That is the level of saturation that the material will reach. So the current now, because H.dl is Ni, it can go to 25 to 50 times the usual current, which is very bad. There would be serious losses that would be happening, and there are 2 to 3 things which will happen. So first of all, the winding can get burnt, right? Because such a high current is flowing. So this is a typical graph of inrush current. So what happens is, in the starting 0.2 seconds, the current peaks like anything, and then it starts to stabilize. Right, as eddy current and hysteresis losses try to damp out that doubled flux, it damps down. And you can see within 0.2 seconds or even within 0.1 seconds, the current has become sober. Within 100 milliseconds, the current has become sober. So there is not much loss actually. And this is good because inrush current cannot be avoided. Until now, there has been no way to avoid this inrush current. There is no protection against it. But what you could do is you could make the bracing of the transformer very nice. So what is bracing? See, you have B, you have I. So there would obviously be some force that would be acting onto your winding. Obviously the force would go net to zero, but it would be trying to pull the winding apart. Like it would be like two equal forces acting in opposite direction. They are cancelling out, but they are still producing some stress. Now the transformer can handle the normal stress, but if you double B and 50 times the I, it is basically having 100 times that stress. So the bracing that you put there to keep that winding intact, that should be good enough. The bracing should be strong. And this high current that we are seeing here, this is for 0.1 second, right? If it goes for like 1 second, you know that this is not inrush. There is something else going on. There has some fault occurred. There is some short circuit that has occurred somewhere in the circuit, somewhere else, not here, somewhere else. But that somewhere else fault is causing a lot of current to flow through the transformer, and its windings are getting burnt. So to stop that, you put protective relays which get tripped. So obviously you put the relay such that it doesn't get tripped by inrush current, but you make sure that the relay, after it senses that, like, 0.4 seconds, 0.5 seconds have gone away and there is still such a high current flowing, then the relay decides, okay, I will have to trip. So you have to design relays like that, and that's called transformer protection. So this is the end of the 5th video. Thank you.